P4 is a naturally occurring form of phosphorus. When elements appear in more than one different form in nature, we give them a fancy word. What's that word?
Isotope.
It's not isotope. It's nearly isotope. It kind of rhymes with isotope. Poly. It's allotrope. Isotopes are the same atom with the different number of neutrons, neutrons not having an entire purpose inside the nucleus other than to keep the protons away from one another. Protons determine what the character of the atom is. But carbon can exist as diamond or graphite or C60 in the spheres. Those are allotropes of carbon. Phosphorus, one of its allotropes is P4. P4, phosphorus, is a solid, and it will react with 6 molecules of chlorine gas, chlorine molecule, Cl2, to make 4 molecules of PCl3. Phosphorus trichloride is a liquid. Okay? So let's write its K expression down. Okay. Here's the concentration of the products divided by the concentration of the reactants, which equals product. I only have one product, and it is PCl3. And I'm going to raise that to the power 4, because there are 4 molecules of product. And then I'm going to divide that by the concentration of the P4, and then I'm going to divide it by the concentration of chlorine gas, raised to the power 6. But then I'm going to get my red marker out and say PCl3 is a liquid and P4 is a solid. So they do not appear in the K expression. So my value of K is 1 over concentration of chlorine raised to the power of 6. Okay, one last kind of theory practice before we start putting numbers into these, looking at concentrations and finding missing numbers. And some of those are straightforward, and some of them require a little bit of thinking. It depends on how they write the question and what they look at. Now, remember when we looked in chapter in kinetics about reactions that followed on from one another, and that the overall reaction was the sum of the 2 elementary steps. That also will be on the test tomorrow. Determine which of those 2 steps is the rate determining step, and what perhaps the rate law of the overall reaction is. Okay, if I have, let me see how I'm going to write this. If I have 2 consecutive reactions, let's say A reacts with B. And I'm leaving space right here to quantify that I might have A molecules of A and B molecules of B, like we did before. A and B are going to combine to make C and D. But C and D, actually they have an affinity for one another, and they themselves are going to combine and make E and F. So I have two steps right here. I have that step, and I have that step. Let's look at step 1, and then we'll look at step 2, and then we'll look at the overall and see how our mathematical representation or symbolic representation of the first step and the second step, when you combine them, equals that last one, the overall. So let's have A molecules of A react with B molecules of B to make C molecules of C and D molecules of D, which ultimately will make E molecules of E and F molecules of F. Okay. If they're all one, which is what I'm going to end up doing, then no harm done. All right, let's look at step 1. Step 1, K1 is product divided by reactant. So the product of step 1 is C and D. I'm going to multiply those together. They should be raised by the coefficients. And then divide by the reactants in step 1. If I look at step 2, is it better for me to write them on top of each other or side by side? Doesn't matter. K2 describes this, and the products in step 2 E and F divided by C and D. Okay. So step 1 represents A and B going to C and D, and step 2 represents C and D going to E and F. Now, if I take line 1, let me subtract line 2 from it. Line 1. A and B are reactants, C and D are products. And here's line 2. C and D are reactants, and E and F are products. If I take line 1 and I subtract line 2 from it, they cancel. line 1, when you subtract line 2 from it, gives me the overall. Okay. Oh. So, to get to the overall reaction, I subtract this reaction from that reaction to give me this overall reaction, and therefore I have a K that goes with it. What have I actually done to the numbers though? Because the value of K is not K1 minus K2. It isn't. This is what happens if you subtract reaction 1 from reaction 2. So we'll put minuses there. Let's look. K overall equals E F over A B. Let's break it out into what K1 and K2 are, right?
Are these all still raised to the power of their?
Yeah,
normal?
I may come back and scribble them in. It doesn't make this any clearer right now if I write all of those coefficients and superscripts in. But know that they are there. And in the real world case, they have to be taken care of. Okay. So, algebraically, if I want to make line 1 and line 2 give me the overall reaction, I subtract line 2 from line 1, which will lead me to what the overall is. Hey, there are my reactants, they go in, C and D appear to be intermediates. You make them, and then they go away. And then I make E and F. So C and D are intermediates, but I can't make them mathematically go away by subtracting them in terms of equilibrium constants, because one's a numerator and one's a denominator. But I can make them go away by multiplying them. If that is a multiplier right there, then that C and that C cancel each other out. And that D and that D cancel each other out. And this is which way did I write that? D? Yeah, that's K1. Q2. So K overall. So the reactions subtract the value of the equilibrium constants multiply. Okay? So if both of those are big numbers, then two big numbers multiply each other and you end up with a nice big number. If one of them's a big number and one of them's a little number, then they multiply, and you have a reaction that zooms to a place and then kind of limps to the end. Or if one of them's a decent number and one of them's a very small number, then you end up with a really, really small number. So a small number in here will completely deflate what it is that you're looking at. And what we'll see in the next chapter, because we're going to use this specifically to look at acids, is that in an acid like H2SO4, which has two H pluses to give, that the equilibrium goes in two steps. And we'll find that K1 is much, much bigger than K2. And we'll hold back on that until it comes up. But I did notice in reading the chapter a little while ago that this is not done at all in this chapter, and it's done in just a mention in the next chapter. And it's something that we need to describe now before we start getting into putting numbers into these calculations. That if the reactions go back to back, yes, all you have to do is subtract them. But in order to get to this, you multiply the values of K. You multiply them. Okay? All right, let's start putting some numbers into these and see what we come up with. So that puts us at about 15.5 in the book, which is calculating equilibrium constants. I think that's about where we want to be. Okay. All right. So we talked a little bit about values of K, and if a value of K can be really, really tiny, and it can be really, really big. So there is an opening here that we are not actually going to use in this chapter, but we will use in the next chapter. What do you do with numbers if my value can be anything between 1 times 10 to the negative 40 and 1 times 10 to the plus 40? Those are that's an enormous range. What should I do with that range? That's an uncontrollable range with very, very small numbers that people don't understand and very, very large numbers that people don't understand. How do we make large variations in number less scary?
The log.
We take the log of those numbers. We're not going to do it in this chapter, but we are going to do it in the next chapter. So a log will turn a change in 10 times into adding 1 to the number. Okay. And that'll come up. So we're not going to use pK right now. We're not going to take the log of K, but we will in the next chapter when we look at acid concentrations. Okay, so the value of K can be big or small. Big means it favors the right-hand side. Small means it favors the left-hand side. And what value will K be if it's slap bang in the middle? have a reaction that says reactant turns into product. And my equilibrium sits right in the middle. What's the value of K going to be? It's not going to be 0. The number of reactants equals the number of products.
1.
It'll be 1. Is there a time when the equilibrium constant can be equal to 0? No. No. In the case that we saw a few minutes ago where K equals 1 over the chlorine concentration raised to the power of 6, we have the possibility that that number is as close to 0 as you're going to get. It's going to be there are occasions where that would be a really, really tiny number. But no, it shouldn't be 0. Slap bang in the middle, your value of the equilibrium constant is 1. So that's your yardstick. Okay, let's find some missing numbers. Okay. So here's a question. I have an equilibrium that says chlorine gets converted into 2 chlorine atoms in the gas phase, and that at 25 degrees Celsius, K equals 1.48 times 10 to the negative 38, no units. Really small number. Really, really small number. So, what am I looking for? Got to add an extra phrase in there. If the chlorine concentration equals 0.76 moles per liter at equilibrium, because some questions are going to give you the equilibrium concentration. Others are not. Others are going to give you the concentration that you start with before the reaction gets to equilibrium. Those ones are a bit more of a work through. So at equilibrium, the concentration of chlorine gas molecules is 0.76 moles per liter. Find the missing concentration of chlorine atoms. Okay, are we expecting this number to be a big number or a small number? This is a very, very small equilibrium constant. The thing that it's asking me to find is the concentration of product. I'm going to put less than a mole of reactant in. Now for every mole of reactant that I put in, I get 2 moles of product out, and that's going to appear in the calculation as a square term coming up in the equilibrium. But this is so far to the left that what we should be expecting is that you should have a very, very small answer. If your answer comes back as a big number, you should doubt what you've done and you should go back and fix it. Okay, so what you do is you write, look, I know what I've got right here, product, reactant. product, reactant. And I now know that 1.48 times 10 to the negative 38 equals. I know what one of those I know what one of these concentrations is, because it's in the question. Okay. Okay, so I have the value of K equals the square of the product concentration divided by 0.76. So if I took my 0.48 times 10 to the negative 38 and multiplied it by 0.76, that would give me the concentration of the chlorines squared. So I've got to figure out what that number is. Get on your calculator and find out that that is 1.06 times 10 to the negative 38. And that's going to be equal to the square of the chlorine concentration of atoms. Take the root . Now would give me the chlorine concentration. And the root of 1.06 times 10 to the negative 38 equals? The thing with exponents is when you multiply them, the exponents add. So 10 to the 2 times 10 to the 2 equals 10 to the 4. And when you divide them, they subtract. So the root of 10 to the negative 30, oh, I'm missing an 8. 38 should be half of 38, which is 19. So my answer should come out something times 10 to the negative 19. And if it doesn't, I'm going to question what I did on my calculator. That is the number you should, oh. And again, if this is a 10-point question, how many points have I earned? I've shown all my work, but I haven't written the units in, and I didn't leave space for it, so I have to erase it and write it again. Moles per liter. Okay, the deal, again, with exponents. Think of this backwards. Instead of taking the root, square this number. If I square that number, the exponents add. My 19 and another 19 equals 38. And that is a tiny number. So in solution, in equilibrium, actually it's not in solution, it's in gas. In the gas mixture, there is very little of this, very little. Okay. Let's see, I've got some more examples. I should have some more. Here's an example of me giving you the equilibrium constant and a concentration, you finding the missing concentration. If I give you all the concentrations, you should be able to find the constant. Question. Here we go. Carbon dioxide is a gas, and it reacts with chlorine, Cl2, which is a gas, and it makes COCO2, which is a gas. And that balances. At equilibrium, the concentration of carbon dioxide is 1.2 times 10 to the negative 2 moles per liter. Concentration of chlorine gas is 0.054 moles per liter. And the concentration of COCl2 is 0.14 moles per liter. Find the value of Kc. Okay. Let's figure out what K is expressed as. K is products over reactants raised to the power of their coefficients, which gives me the concentration of COCl2, CO2, and Cl2. Okay? And then just plot the numbers in, because there's no square terms here, there's nothing fancy. All the coefficients are 1, everything's raised to the power of 1, so you just put the numbers in the boxes. So K equals concentration of COCl2 is 0.14 divided by 1.2 times 10 to the negative 2. I've never been a fan of that. Times 0.054. I mean, why would they do it for one and not for the other? They didn't do it for this. I don't get it. Number.
$216.
Yep. Okay, this is a 10-point question. How many points have I earned?
10.
10. Shown all my work. Everything's very, very clearly laid out. My answer doesn't have units because my answer doesn't need units. Okay, let's squeeze one more in. This is a KP. I'm not sure I have a follow-up to this, but a follow-up to this would be useful as to convert that KP to KC, which is actually the next step. Different reaction. All right, I have two NO2s in equilibrium with two NOs. These are in the gas phase. This one didn't come with the temperature. It's supposed to come with the temperature. It didn't. This one's going to. I gotta tell you, the value of the equilibrium constant is 158. So 216, 158, both in the same ballpark, telling me what? Product is favored. These reactions make product. The equilibrium is to the right-hand side. That has to be quoted at a temperature, but it's unnecessary for calculation. Okay, if I look at the partial pressure of NO2 at equilibrium, I find out that it is 0.4 atmospheres. And the pressure of NO, nitrogen monoxide, is 0.27 atmospheres. Go ahead and find me the missing pressure. Okay. First thing to do, write the expression for the equilibrium now. Products divided by reactants. Here, we're not talking concentrations because this reaction is being measured by pressure. So I have the pressure of nitrogen monoxide raised to the power of 2. Okay, don't forget to put that term in. Times the pressure of oxygen would be raised to the power of 1. All divided by the pressure of NO2, also raised to the power of 2. Okay, I can just put a few of those numbers in now, or I could rearrange now. In the way that I've done it, I have opted to put the numbers in. Okay. So 158 equals pressure of NO, 0.27. 0.27 squared. I'm going to make that number smaller. This number is less than 1. So when you square it, a number that is less than 1 times by a number that is less than 1 ends up being less than 1. They get smaller. P2 is here. And then in the bottom I've got my NO2. Same thing with that right here. So, at this point, I could have done this earlier. Oh, maybe I'll do it. I could have done this symbolically where I just move this over and move that up and then multiply it out. So all I'll do here is I'll add an additional step. Okay. So here is my PO2. I'm going to isolate that. Here's the 158. I'm going to move this 0.4 squared term across the equal sign, and it'll go from being a denominator up to the top. I'm going to write it out one more time the long way. And then I'm going to move that term across the equal sign, and it will become a denominator. There you go. That should be 158 times 0.16 divided by 0.73. 158 Okay, big number times a small number makes that number smaller, but then divided by a very small number makes my number big again. And because this is a smaller number than that one is, my answer should be larger than the 158. So my answer comes out to be 347. 347 what? Atmospheres. Okay. All right, we're done. 1 o'clock, we'll reconvene and we'll work through the problem set for those of you that can be here. Those you can't, it's going to be recorded and made available to you tonight. In the interim, like if I don't see you, go home steady. The test is only, is it 12 and 13? Was it 13 and 14? Okay, solutions and kinetics. Plenty of stuff. Okay, see you later.